Hey, AP Chemsters, this is Mrs. Vanderwally bringing you another edition of Blank Wall. Today we're going to continue on in section 6.4, where up until now we have talked about just things gaining and losing energy. We talked about Q, which is our heat energy. But this part of the notes are going to talk about what happens when we put two things of different temperatures next to each other. Remember what we said earlier, that heat will always flow from the hot substance to the cold substance. And so if I put, let's say in this case right here, a metal block is initially at 55 degrees Celsius and is put into water at 25. So it says thermal energy transfers as heat from the metal to the water until they're both same temperature. Why from the metal to the water? Well, the metal is hot, it's 55 degrees Celsius. The water is cold, it's 25. So the energy will go from the metal to the water. Let me kind of show you something here. I'm going to draw a little something here, and this would be, in a sense, temperature, and this is time. What happens to my metal block? It starts off at 55, and it's going to do something like this. And here's my water. So here I'll put a little M for metal. So here's my water. It starts off at 25, and guess what? It's going to go up until it's also at 25. I'm sorry, until they both are at the same temperature. So here we start at 55, and here we start at 25. And notice what happens right here. As time goes on, they end up at the same temperature, and that's your T final. So if you recall, when we did MC delta T was final minus initial. They both end up at the same final temperature. And we can use this for, solving for different temperatures, different masses, different substances, whatever the question is asking for. One thing else that is super duper important is the equation over here. It's right here. So Q of the system equals negative Q of the surroundings. That shouldn't be surprising for anyone. So in this case, the metal block is the system. What is it doing? It's releasing energy. It's exothermic. So if this were negative because it's releasing energy, what is the water doing? It's gaining that energy. So isn't that what negative times a negative is? Yeah, it's a positive. So one is always going to be the opposite sign of the other. And that's what allows these things to equal each other out. Okay, so that's how we can make one side equal to the other if you take the negative of it. Because one is always endo, one is always exo. We have to multiply one side by -1 to make the values equal. So let's see how this works. So it says a 32.5 cube of aluminum, initially at 45.8 degrees Celsius, is submerged into 100.5 or 105.3 grams of water at 15.4. What is the final temperature of both substances at thermal equilibrium? Well, what's first of all going to happen? That aluminum is going to give up its energy and water is going to absorb it. So the aluminum is exothermic, the water is endothermic. So once again, we have to have this idea where one is the negative of the other. So what do we want to define our system as? Do you want to define that as aluminum and make the surroundings the water? I think that makes a lot of sense. So everything on the left-hand side is going to be aluminum, and everything on the right-hand side is going to deal with the water. So if I do that, you'll notice that everything here, like I just said, on the left-hand side is dealing with the aluminum, and everything on the right-hand side is dealing with the water. Notice I haven't lost my negative sign. So let's go ahead and plug in the values that we know about. And again, if I'm going too fast, always pause this so you can catch up. But we always said, we already said that the aluminum is here. I had to go back and look this one up. I didn't give it to you in the problem. I'm sorry about that. And notice how delta T is always final minus initial. I still have my negative sign. Here's the mass of the water. We know the specific heat of water. It's always this. And again, final minus initial. Well, what do we know about the final value? It's the same for both. So I went ahead and I put in the initial values for both. And now this is just a simple math equation. What I did next is I multiplied the 32.5 by 0.903. And then I multiplied -105.3 times 4.18. So if you see when I did that, probably maybe if you pause this and you did the math yourself. So 32.5 times 0.903 is 29.3. Oops, hang on. Sorry about that. I grabbed the wrong information there. So again, I multiplied 32.5 by 0.903. I got this. I multiplied these two numbers here and I got negative 440. Kind of a little lazy about sig figs right now. Sorry about that. And now what? Simple math. What am I going to do? I'm going to distribute the 29.3 throughout. I'm going to distribute the negative 440 throughout. And that's where this comes from. So I distribute the 29.3 TF minus, and then multiply these two numbers here, and there I go. So now what am I going to do? I'm going to combine like terms. I'm going to add 440 TF to over here. And I'm going to add 1341 to this side over here. So when I do that, here I get 469.3 TF equals positive 88118. And then I divide both sides by TF, or excuse me, by 469.3. And I got 17.3 degrees Celsius. Now, does this make sense? No, yes, it does. Oh, phew, for a minute I thought it didn't make sense. It does make sense. Holy cow, I almost blew it. Why does this make sense? Well, let's go back to this whole idea again, where I start off with my aluminum here at 45.8, and it's going to lose energy. And here I'm going to start off with my water at 15.4. and it's going to gain some energy. And notice they end up somewhere between those two values at 17.3. Now, notice a couple more things. Notice the water only went up by like 2 degrees, and the aluminum went down by, 28 degrees or so. Why did the water only go up such a little amount? 2 reasons. The mass is a lot bigger, about 3 times more mass than the aluminum had. But what's more important? Your specific heat of water is about 4 times bigger than the specific heat of aluminum. Do you remember what we said? We said that the specific heat is a measure of how much energy it takes to raise 1 gram by 1 degree Celsius. So if I have a lot more mass and a larger specific heat, it's going to take a whole lot of energy to raise more mass and a higher specific heat by 1 degree. So really, I can only go up about 2 degrees with the heat given off by a smaller amount of aluminum at a smaller specific heat. So this does make sense. And this right over here, this value right here I'm kind of circling, that is thermal equilibrium. Okay, let's go to the next page. Okay, problem number 14 says a block of copper of unknown mass has an initial temperature of 65.4. Copper was put in some water containing 95.7 grams of water at 22. When the two substances reach thermal equilibrium, the final temperature is 24.2. What's the mass of the copper block? Notice once again, I have 2 things in contact with one another. And the copper is at a higher temperature, the water is at a lower temperature. So once again, we can use this. This is what we use when 2 things are in contact. The system is going to give off heat, the surroundings is going to gain heat, and again, we need that negative sign to show the math works. So I'm going to make copper my system and my water the surroundings. Hopefully that makes sense to you. So now I can substitute this MC delta T of both substances. So the left-hand side is going to be dealing all with the copper. The right-hand side is going to be dealing all with the water. So the next step was to just plug in all my values that I know about. I don't know the mass. That's what they're asking me for. The specific heat of copper, you could have looked up on, prior page someplace. Here is the final, 24.2. Here's my initial, 65.4. Don't forget your negative, 95.7 grams, 4.18, final minus initial. So this is a pretty straightforward problem. I multiplied by 1.5, and then what? I multiplied these 2 terms together, and then I divided. So why don't you pause this, you do the math, and see what you get. Okay, did you get this? Mass is equal to 37.8 grams. I hope you did. That's what I got. So does this make sense? Well, once again, we had if I were to draw this thing out again, here's my copper at 65.4 and it's losing mass. Here's my water at 22.7 and it's gaining energy. And so notice they both end up at 24.2. Once again, water only went up by a teeny tiny bit and copper dropped by a large temperature difference. Why is that? Well, the specific heat of water is a lot bigger than the specific heat of copper. It's more than 10 times as much. Okay, so what else? I have a fairly large amount of water, and it would make sense that I don't have that much mass of the copper. The temperature of the copper went down only by so much. The temperature of the water only went up by 1.5 grams. So you needed so much mass to raise that temperature of water by only 1.5, and it turns out to be 37.8. So let's go ahead. Why don't you read number 15 and see what you come up with. So pause this and I'll be right back. So what did you get for this, A, B, or C? I don't know about you, but I got C. Okay, why did I get C here? Well, we can plug it into an equation, all right? So Q equals of the system, oops, SYS, there we go, is equal to negative Q of the surroundings, right? That says surroundings. What do we know? The mass of A is twice the mass of B. So I'll have 2B on this side, or not B, huh? You knew that was coming. And here's B over here. But what else do we know? The specific heat capacity of substance B is twice the capacity of A. This is a B right here. Hopefully you saw that. So then delta T and delta T. So what do you notice? That these all kind of cancel out, and it's not going to be closer to one thing or another thing. It's going to be smack dab in the middle. Hopefully you can read that. I'm going to quit here and start a brand new one to talk about work. Okay, so we're going to stop this and watch for the next one. Talk to you later. Bye-bye.